We're going to talk a little bit about our best management practice decision tree here. Basically, it takes all of the infrastructure options that Amber just addressed and breaks them down and more or less gives you a high-level overview of if your conditions are like this. So our first question is your infiltration rate of the soil between 0.7 and 0.5 inches per hour? And then it'll direct you in one way or the other. So depending on your answers, it'll direct you to a few key infrastructures that you should investigate. It doesn't necessarily tell you that these are the only infrastructures that will work. It's more or less just saying these are the primary ones that you should investigate, and then based on your site conditions, and what you're trying to achieve with your project, you can investigate other options. I'll start by I'll just get through this. Since our infiltration rate was greater than 0.5, dropped this down to this level. And then, brought us over here. Our slope was less than 8 degrees, so, or 8%. So, continued us on. We had a greater slope than 1%, so it brought us on up here, and we're trying to achieve habitat, growth of plant life, and hopefully more flowers and bugs, butterflies, bees, and stuff. So that brought us to options 1, 2, 6, and 9, which are rain gardens, rain barrels, permeable pavement, and green roofs. And then depending on, we investigated all of these infrastructures. We found that rain gardens would in fact be able to be implemented here relatively easily. Rain barrels also very easily implemented. We implemented them on about half of the houses on the street, implementing only 2 rain barrels on each house. Typically, you can have up to 4 rain barrels on each house, so we're trying to be conservative with our estimates. And basically, we only implemented on half of the houses because it's homeowner-based, whether they'll allow you to put it on their house or not, and it's homeowner participation. Let's see, permeable pavement. There were a few areas where cars were currently parking in the grass, and it had turned it into more or less swamp areas, as you can see pictured. Over there. Yeah, there's 2 lower pictures right there. So we wanted to implement permeable pavement there. We felt there would be low enough traffic that it wouldn't be disrupted, but it would be a good spot to implement it. And then green roofs, like Amber said, you have to investigate the houses to find out whether they're structurally sound enough to support a green roof. There's also maintenance that you have to perform on them annually or semi-annually. And that requires people getting up on the roofs to make sure that there's no wood rot or damage or anything on their roof structure, so that could present as a safety hazard to the homeowner. And we didn't feel that was something that we wanted to do in our particular site. We did also end up investigating bioswales, dry bioswales, and found that we did have the space, and that our infiltration rate, since it was higher than 0.5, bioswales are typically recommended for between 0.27 and 0.5 inches per hour infiltration rate. But they will work with greater infiltration rates than that. The major recommendations for if you're in with that infiltration rate, then that's something that you do need to try and implement. Since ours was greater, we were able to, but it wasn't one of the primary recommendations. So that's what we went with in our design, and then I'll hand it off to Matt.
All right. As an extension of our decision tree, we developed a model for a system for ranking different properties. Like a cutout of our full ranking system is on this poster, but it's also in the handouts. Basically, we want a ranking system that will identify the properties that would be most effective. If we were to install rain bars and rain barrels, it would provide the greatest benefit for the entire subdivision. So basically, this would be used to help determine where to spend resources, whether that be time spent trying to influence individual homeowners or any financial compensation that might be paid to them, depending on how it might benefit the entire subdivision. So basically, rain barrels was a more cut and dry process. It was we basically just ranked them as a function of the building size. We figured more than the building footprint, more rain run off the roofs would be captured by the rain barrels. The rain garden ranking system was a little more intricate. It basically put a premium on the amount of space that would be available to install rain gardens. It would put a premium on total parcel area. Believe the less amount of impervious surface possible would also yield the best result. The variables that were considered were the impervious area, the total area, the property low point, and the distance to the local minimum, like a local low elevation of the road. So basically, trying to find the properties with the most space to build with that would encounter most runoff water. So we use that in our design, our final design of our subdivision.
And then using the rating system and the decision tree, we did a case study on Stewart Avenue in Madisonville. So this diagram just shows Stewart Avenue, and as you can see from the pictures, they do not have any curb and gutter, so drainage is a problem on the street. And what you can see that at the low point there is issues alongside the street, and people are still in park there. So there are some drainage problems along the street. And now I'm going to talk about proposed design.
All right. You were just touching upon the bioscope real quick. You know, some of the decision tree, one of the reasons why we chose it is, as you can see right here, there's already a swale on the side of the road used to convey to the storm drains, but it's got pretty neglected, so it seemed like a pretty good idea for us just to kind of rehab that swale, turn it into a flat swale. But again, we use these BMPs here, and we try to use them in accordance with the MSP Stormwater manual as best as possible, and to the best of our knowledge, which is a pretty good read. Okay, so the first thing we started with is bioswale here, which you can see on this poster. And this takes water down here to 4 inlets, which is this structure right here. So these are low points, so the water will run down the swale into these inlets and exhaust into this dry creek bed right here. And these permeable pavements here, these are actually sloped to drain out. It's going to fall in there. There's not too much water captured, but it's back sloped, so it'll just drain right in there. And this one comes here and out probably towards low point down here. But to get an idea, for example, the manual says that you got to design a swale to accommodate a 10-year storm, and we did that using Manning's equation, which is this page that you know, and we used trapezoidal channel because that's recommended by the EPA for bioswales, and pretty cool Excel sheet giving the side slopes, and you enter a base longitudinal slope, which we calculate for the street based on the topography, and Manning's coefficient, which we used for bioswale